Hi, my name is Amy Binder, and I'm going to tell you about the CMB-S4 experiment and how we use it to explore the microwave sky. So observing the microwave sky really enables broad science. This graphic is showing our understanding of the history of the universe with the Big Bang on the left and present day over on the right. Now, in between, we had a period of recombination. This is where the cosmic microwave background originates, followed by dark ages, reionization, and then a fully ionized universe where stars, galaxies, galaxy clusters, and all the other beautiful things in the night sky formed and grew. Now, turning back to the cosmic microwave background, because it originates about 400,000 years after the Big Bang, it really gives us a snapshot of the early universe. And you can see what that snapshot looks like. This is an example of a CMB map. The CMB also contains the imprint from structure formation that happened throughout the late universe. And so CMB observations allow us to study both the origin and the evolution of the universe, asking questions about inflation, neutrinos, dark energy, and beyond. Now, if that's not enough to get you excited, maybe this will. The CMB also acts as a backlight for galaxy clusters that formed throughout the universe. So you see here on the left an image of a galaxy cluster in optical and X-ray compared to what it looks like in a microwave map, a little dark spot, as it is in fact backlit. Additionally, microwave maps also contain emissive sources. So you see down here 3 examples of microwave emissive sources. These are probably either active galactic nuclei or dusty star-forming galaxies. And so we're able to learn a lot about those sources, but as well, there's a whole new space opening up of microwave transient events. So CMB-S4 is hoping to observe all of these effects. There is strong community support. In particular, we got a very nice recommendation from the Astro 2020 Decadal Survey, calling out the broad science case. So the experiment, let me tell you a little bit about the experiment itself. We've optimized the design to deliver on 4 key science goals, first of which is a transformational measurement to detect or rule out many of the models of inflation, which is a theorized period of exponential expansion in the very early universe. We want to discover or rule out new light particles that are predicted by beyond standard model theories of physics. We want to map all the matter in the universe, dark and luminous, to learn about structure formation and its underlying physics. And then finally, as I said before, open up this discovery space of millimeter wavelength astrophysical transients. And these 4 science goals lead us to a design that includes both large and small telescopes sited at the South Pole, as you see down here, that will focus in on a smaller patch of sky that we refer to as the Ultra Deep Survey, and then 2 large telescopes sited in Chile that will map a large fraction of the sky, about 60%, to do, for example, some of this matter mapping and astrophysical transient searches. Now, why is CMB-S4 at the South Pole? Well, the South Pole offers some very important advantages, the first of which is just a geometric advantage. Because sources stay at a constant altitude above the horizon all day, 365 days a year, you can naturally map a given patch of the sky much faster. It ends up being about a factor of 2.5 times advantage. The South Pole also has the best atmospheric properties for any millimeter wavelength site that is developed. So down here on the right, you see a plot showing fluctuation power in atmospheric water vapor, which introduces noise into microwave data. And so by having exceptional stability at the South Pole, it really limits the impact of that noise on our measurements. You can see here the black line shows the South Pole compared to other sites. Dome is a little better. Down here in blue, for example, is the Atacama Desert in Chile, which is our other site. One piece of technology that I wanted to highlight quickly is our superconducting detectors, because these really are key to CMB-S4's extraordinary sensitivity. So we're planning about 500,000 superconducting transition edge sensor detectors. These are an established technology. There's a lot of heritage from their use in past and current CMB experiments. The real challenge here is simply scaling up to this quantity of detectors. You can see down here, this is a CAD model of what our detector module will look like, with feed horns on the top, coupling light in onto a detector array that sits behind it. This is a photograph of a real CMB-S4 detector array. zooming in on a single pixel over here, you see the antenna that couples the light and then distributes it out to 4 of these individual TES detectors. So I want to end by just saying thank you. It's really a vibrant community. The CMB-S4 Collaboration has over 400 members from 116 institutions and 18 countries, and I look forward to any questions.